Greetings. We spent some time discussing how to symbolize arguments, how to represent ordinary arguments in English, statements as premises of arguments and then their conclusions, in the form of a series of symbols. Today, or this week, we'll be starting on introducing a simple and powerful technique that will enable you to check in many cases whether an argument is valid or not. This is an important stage. We need to work with this and be careful with it. So we'll introduce it slowly. The method is called the method of truth tables. What we're going to begin to do is we're going to learn how to construct a truth table for an argument. We can begin by reminding ourselves of some basic meaning. First, as you all remember, there are atomic statements. An atomic statement is just a statement that doesn't contain any other complete statement as a part. And we can symbolize them with single capital letters, like this. M or S or B. Mary went to the party. Sam went to the party. Betty went to the party. Each of those is a single atomic statement. But once you've got atomic statements, then you can create compound statements by combining them with logical operators and combining them with one another in logical operators. For example, like this. It's not true that Mary went to the party. Either Sam or Betty went to the party. If Mary went, then Betty went. Now, the interesting thing about these compound statements is that they are truth functional. What that means is that you can figure out whether the compound statement is true if you know whether the atomic statements that are part of it are true. The truth value, whether it's true or false, is completely determined by the truth value of its components. For example, looking at the examples of negation and conjunction. Negation is really pretty easy. Take a look at this. We have a statement which we're representing as P, and its denial or negation is not P. Now under P, you see a column there, and it has T and F for true and false. Those are all the possibilities. For P, it can be true, or it can be false. What about for the negation of P? What about for not P? Well, if P is true, then not P is false. And therefore it's marked with an F on that line. On the other hand, if P is false, then not P is true. That's pretty simple. That's the simplest case of a truth functional statement, where you have just a single atomic statement and a single logical operator, the negation or the not operator. But we can go beyond that, of course, and we can talk about cases where you've got more than one atomic statement and how they're related in various ways. Let's look to another very simple case, namely conjunction. You remember, that's the AND operator. Notice what we've got over here. There are two columns to the left, the P and the Q. And if you look, there's the Q column, which goes true, false, and then there's the P column, which goes true, true, false, false. Now, if you look at those and think about it for a moment, forget the stuff over on the right now. Notice that that includes every possible combination of the truth values of P and Q. It includes the case where they're both true. It includes the case where P is true and Q is false. It includes the case where P is false and Q is true. and it includes the case where P and Q are both false. Now, if you've got that, take a look over on the right-hand side where we've got P and Q, and we want to know what is that? What is the truth value of that? What is the truth value of that given that we've got these other truth values here? And it's pretty simple. P and Q is true only when P is true and Q is true. And that's the first line. It's marked true under the AND operator. But if P is true and Q is false, well then P and Q is false. If P is false and Q is true, then P and Q is false. If they're both false, then P and Q is false. This should be pretty straightforward. If I say Sam went to the party and Betty went to the party, the only way that's true is if Sam was there and Betty was there. If Sam wasn't there, it's not true that Sam and Betty went to the party. If Betty wasn't there, it's not true that Sam and Betty went to the party. And if neither one of them was there, it's not true. The only way a conjunction can be true is when both the component atomic statements are true. And so what you've got, and this is typical for a truth table, in fact this is always for a truth table, what you've got is you've got an assignment of truth values that tells you whether the compound statement is true depending entirely on the truth values of the atomic statements that make it up. And you can tell for every single case whether the compound statement is true once you know the values, the truth values of the atomic statements. Let's go beyond this. Let's take a look at disjunctions. For example, Alan is in class or Betty is in class, A or B. Then you'd get a truth table that looks something like this. Over on the left again, you have the column that goes true, false, and then true, true, false, false, and that includes every possible combination of A and B being true or false. Over on the right, you have the statement symbolized, the compound statement, A or B, and you have a value assigned for each of those combinations of the truth values of the atomic statements. For example, well, if Alan and Betty are both in class, then surely Alan or Betty is in class is true. If Alan's there and Betty's not, true again. If Betty's there but Alan is not, it's true again. What if neither one of them is there? Well then, it's false. And so that's what you've got. You've got A or B is true except when both of the disjuncts, A and B, are both false. Pretty clear, pretty simple. Let's take another step. We haven't talked only about conjunction and negation and disjunction. A step beyond that is talking about. Let's go on and say something about conditionals. As you remember, a conditional is just an if-then statement, having the form if P, then Q, where P stands for the antecedent and Q stands for the consequent. I'd like to remind you of three important features of conditionals. The first one is that it has to support modus ponens arguments. When you have if P then Q, and you also have P, you can conclude Q. Once you've got the conditional and the antecedent of the conditional, you can conclude the consequent. And that's a valid argument. Second, conditionals also support modus tollens arguments. When you have if P then Q and not Q, you can conclude not P. Notice that this means that at the same time you've got if P then Q is true, at the same time that not P is true and not Q is true. Third, and this is a very important feature, when you've got P being true and Q being false, you can conclude that if P then Q must be false. For example, suppose somebody gives you this conditional. They say, if it is raining, then the road stays dry. And you look outside and you see, yes, it is raining, so P, the antecedent, is true. But contrary to what they said, the road is not staying dry. The road is getting wet. So Q is false, the consequent. Well, when the antecedent is true and the consequent is false, then it must be the conditional that is false. In other words, if P then Q will turn out to be false. All of those are features of ordinary conditionals, the kind of conditionals that we use in everyday language. Now, if we go on a little bit from here, we're going to introduce a new. Logicians have defined a particular kind of conditional, which we'll call a material conditional. It has all three of the features that we just talked about, but it's still not quite like the conditional in ordinary English. We're going to put it this way. For a material conditional, which will be symbolized in this way, P arrow Q, or R arrow S, or whatever, a material conditional is false only when the antecedent is true and the consequent is false. That's that third feature that we talked about. For a material conditional, that's the only time that it is false. For example, look at this one. If snow is white, then grass is orange. We might represent it this way. S arrow G, or if S, then G. But obviously, we all know that grass is not orange, and so, but while snow is white, and so we know that that's false. That sounds pretty much like ordinary conditionals. The key difference is when you say otherwise, it's true. Material conditionals are true in every other case. Now, there are some differences in this usage and our ordinary language usage, so it's important not to confuse them. We will be talking about material conditionals because they're simply very useful for doing logic. One of the differences, I'll just mention it in passing, is that we normally think there has to be some kind of connection between the antecedent and the conclusion. For example, we wouldn't normally accept something like, if snow is white, then Obama is president. That's a perfectly good material conditional, though, because it has a true premise, or a true antecedent, and a true consequent. But to us, in our ordinary language, it doesn't seem like there's any connection against them. It seems like, well, snow could still be white even if somebody else were president. But I don't want to go into that a great deal. The main point is just to understand what a material conditional is. And we'll proceed by looking now at the. Here we have the truth table for the material conditional. As before, we've got every possible combination of true or false for P and Q. And, as promised, we have only one false on the right-hand side. That's when P is true and Q is false. But while we're looking at it, I'd like you to take a notice that the other properties that I said were important for a conditional are there too. If you look at the first row, you'll notice that the conditional if P then Q is true and P is true, then Q turns out to be true also. That's the modus ponens property. If you look at the final row, the fourth row, you'll notice that if P then Q can be true while P is false and Q is false. That's the modus tollens property. If you're not completely clear on this, it might be useful to go back and look at that and think about that again. We've got all three of these properties, these important properties for a conditional, embedded in the truth table for the material conditional. The only thing that might be a little bit odd, or one of the things that might be a little bit odd, is that we have when P is false and Q is true, then we say that the material conditional is true. And I don't want to dwell on this or spend a lot of time on it. I'm just pointing it out and saying this is the way we will do it. It turns out to be extremely useful to use this table for the material conditional. As you might imagine, if there's a material conditional, there's also a material biconditional. Let's take a look at it. Here is the basic truth table for the material biconditional. The basic result is that when you've got P, if and only if Q, then that's going to be true when P and Q are both true and when they're both false, but not if they're mixed. Now, the basic reason for that is that the biconditional, as the name might suggest to you, is really a combination of two conditionals. It's if P then Q plus if Q then P. Or we can put it a different way and we can say that it's the combination of if P then Q and if Q then P. Now, what we want to do when we go through this, and we'll end up in the same place, what we want to do is we want to start filling in the rows. Let's start filling in the rows under if P then Q, when we've got the truth table with the P's and Q's over here on the left. What we'll get is we'll get true, false, true, true. That's just the way the truth table for if P then Q goes. Now we need to get the truth table for if Q then P. And using the same things over on the right-hand side, on the left-hand side, we'll get this. And if you look under if Q then P on the right-hand side of the diagram, you'll see it goes true, true, false, and true. That is, it's true when both P and Q are true. It's true when Q is false and P is true. It's false when Q is true and P is false. And it's true when they're both false. Now we want to put them together. You can pretty much guess where this is going. If you have a true and a true, this is the first row. True and true is true. You have a false and a true on the left hand and right hand side of the right hand block. That's false. You have a true and a false. That's false. And then the last one, you have a true and a true, and that's true. Notice you've got going down the middle and highlighted in red, you've got the table for the material biconditional. That's because if P then Q and if Q then P is the very same function as the material biconditional. Now, so far we've just been going through the basic operators and talking about them. There's a lot more that we can do with this truth table method, and we'll begin to get to that in our next lesson. But for now, this is enough material to begin to get familiar with. Learn how these truth tables for the basic logical operators work. And I'll be talking to you again soon.